Bismillah. Hello everyone, my name is Salah Atiyah. I'm a condition monitoring and reliability specialist. Today we're going to talk about the gearbox fault analysis as a part of the fault analysis series. My name is Salah Atiyah, condition monitoring and reliability specialist, Cat4 vibration analyst. First, we're going to talk about the gear types and design. The first type is the spore gear. The spore gears connect parallel to the shaft, and the teeth cut are parallel to the shaft as well. There is no axial or thrust forces. Also, they consider a bit noisier and have more noise than the other gears. The second type, which is the helical gears, gears are connected parallel to the shaft, same as the spore gears, but the teeth are cut at angle to the shaft. You can have radial and axial forces, and it's used on in high-speed machines, and the angle cut can be up to like 30 degrees, and there is a couple of types. There is single helical gear and there is double helical gear, which is called herringbone. More smoother and help in reduction on the axial load. You have also the bevel gears, which is convert or transmit power between two intersecting shafts, usually 90 degrees apart. Two types of bevel gear, straight and spiral. The spiral is more smooth and better teeth meshing and used for higher loads. Also, you have the worm gear, the worm gear, which is have the power transmission reduction of the axial load. Could be difficult to analyze. And the ratio will be the number of teeth of the wheel divided by the number of threads of the worm. The gear meshing frequency, all of us know this, which is the number of teeth multiplied by the shaft speed. Also, they have the output speed, which is the input speed multiplied by the input number of teeth divided by the output number of teeth. Also, you have something called the gear assembly phase factor. The gear assembly phase factor is a pattern which is caused the gear wear problems and which result on having some subharmonic component of the gear mesh. The gear wear and the common factor. All gears should be designed with the prime numbers of teeth, like 1, 3, 5, 7, 11, and so on, which will enable a certain teeth of the first gear to mesh with all teeth on the second gear. Before contact the first teeth on the second gear for the second time, and that happens with all teeth, and by that way we can be sure that we have equal load distribution or equal load meshing load at all teeth and even wear at all the teeth in your gear. Sometimes this does not happen or this is not the case. So we'll have a couple of examples. Like for example, if you have 33 teeth gear and 21 gear, 21 teeth gear, what will be your common factor? Like let's say for the 33 one will be 1 multiplied by 3 and 11, all the prime numbers, and the 21 will be 1 multiplied by 3 and 7. So a tooth on one gear will mesh with every third tooth on the other gear. Because in this case you will have your common factor will be 1 and the 3, and the product of the common factor will be 3. But if you have 30 teeth gear and the other one 18 teeth gear, so the first one, if we get the prime numbers for this one and divide it to numbers, it will be like 1 multiplied by 2 multiplied by 3 and 5. And the 18 teeth will be 1 multiplied by 2 and then multiplied by 3 and 3. So you will have common factors like you have your 1, 2, 3, 1, 2, 3. So the product of the common factor will be 1 multiplied by 2 and 3, it will be 6. In that case, the tooth of the first gear will mesh with every 6 tooth in the second gear. You also have the gear assembly phase factor, which is the gear mesh divided by the product of the common factor. Also, you have the hunting tooth frequency, the frequency which one tooth of the first gear met or contact the same tooth on the other gear every time. The hunting tooth frequency will be the gear mesh multiplied by the product of the common factor divided by the number of tooth for the first gear multiplied by the number of tooth on the second gear. You have something also called ghost frequency. It is a frequency normally appear when you got new gearbox as a result of machining or surface finish problem, and it disappear by short time from running the gearbox. The gear tooth wear, which is how you see it on the spectrum, you will see the running speed side bands around the gear meshing frequency with the second and the third harmonics. Sorry. You will start with the first gear mesh frequency, then you will start to have side bands, then you will see the second harmonic, and then side bands arise, then the third harmonic, and then side bands arise. And this is as deterioration of your gear wear problem. Also, you can have misaligned gear pattern, which you will see the gear meshing frequency multiplied, surrounded by side bands and its second harmonic and third harmonic. Normally, you will see the second and the third harmonics with higher amplitude than the first harmonic of the gear meshing frequency. Also, you can see the hunting tooth, as we said, which will be the gear meshing frequency multiplied by the product of the common factor divided by the number of tooth of the first gear and second gear. And also you can see the cracked or broken teeth, which is very important. Use your time waveform in this condition, which normally that defect will appear on the gearbox time waveform as a sharp high amplitude impact at the running speed shaft frequency with high crest factor value. And it's very important and very essential when you do analysis for the gearbox. You must have a look on the time waveform. This is a couple of gearboxes I worked on, and I put the calculations of how you can calculate the gear meshing frequency. It's multiple stages gearboxes, how you calculate the gear assembly phase factor and the hunting tooth frequency. For example, we can have a quick look. This is your first input gear, which is the bevel gear, which is this one, and then your second gear, which is here in blue color, and the third gear, which you have this one in orange color here, which is meshing with this pink one. This is the third gear, and then the third and the fourth gear, which is this one in green, that one on the same shaft, which is this is your first stage, second stage, and then you will go for your third stage, which is meshing with the big gear, the yellow one, and then you will have output shaft. So you'll have the gear meshing frequency for the first one equal 17 multiplied by 24.6, which is the input shaft speed, and 17 is the number of tooth for the first gear. And then you get the speed of the second shaft, and then you have the number of tooth for the third shaft. You get the speed for the third shaft, and then the fourth shaft. You can pause the video at this slide, and then you can have a look on the different calculations, different gear mesh, because you can have, like in this case, you have 3 gear meshing frequencies. So you can have a look on it, and you can have a look on the gear assembly phase factor calculation, hunting tooth frequency, and you have a couple of gearboxes, so you can have a look on them. It's very interesting. This is the last slide. It's talking about if you have a broken tooth on your gearbox, like this one, you can see high amplitude impacts in your time waveform. This is the one we talked about. And also you can see this high spikes of the circular plot, which is very good plot, can be used in like the MHM software, in the Emerson, or the SPM software as well. It will be very nice to show the broken tooth and the impacts on the system because of the broken tooth. That's all for today, and thanks for watching. Please like, subscribe, and share, and I hope you enjoyed the video. Thanks.